Natural gas, also called fossil gas or simply gas, is a naturally occurring mixture of gaseous hydrocarbons consisting primarily of methane in addition to various smaller amounts of other higher alkanes. Low levels of trace gases like carbon dioxide, nitrogen, hydrogen sulfide, and helium are also usually present. Natural gas is colorless and odorless, so odorizers such as mercaptan, which smells like sulfur or rotten eggs, are commonly added to natural gas supplies for safety so that leaks can be readily detected. Natural gas is a fossil fuel and non-renewable resource that is formed when layers of organic matter, primarily marine microorganisms, decompose under anaerobic conditions and are subjected to intense heat and pressure underground over millions of years. The energy that the decayed organisms originally obtained from the sun via photosynthesis is stored as chemical energy within the molecules of methane and other hydrocarbons. Natural gas can be burned for heating, cooking, and electricity generation. It is also used as a chemical feedstock in the manufacture of plastics and other commercially important organic chemicals and is less commonly used as fuel for vehicles. The extraction and consumption of natural gas are major and growing contributors to climate change. Both the gas itself, specifically methane, and carbon dioxide, which is released when natural gas is burned, are greenhouse gases. When burned for heat or electricity, natural gas emits fewer toxic air pollutants, less carbon dioxide, and almost no particulate matter compared to other fossil and biomass fuels. However, gas venting and unintended fugitive emissions throughout the supply chain can result in natural gas having a similar carbon footprint to other fossil fuels. Overall, natural gas can be found in underground geological formations, often alongside other fossil fuels like coal and oil, petroleum. Most natural gas has been created through either biogenic or thermogenic processes. Biogenic gases formed when methanogenic organisms in marshes, bogs, landfills, and shallow sediments anaerobically decompose but are not subjected to high temperatures and pressures. Thermogenic gas takes a much longer period to form and is created when organic matter is heated and compressed deep underground. During petroleum production, natural gas is sometimes flared rather than being collected and used. Before natural gas can be burned as a fuel or used in manufacturing processes, it almost always has to be processed to remove impurities such as water. The byproducts of this processing include ethane, propane, butanes, pentanes, and higher molecular weight hydrocarbons, hydrogen sulfide, which may be converted into pure sulfur, carbon dioxide, water vapor, and sometimes helium and nitrogen must also be removed. Natural gas is sometimes informally referred to simply as gas, especially when it is being compared to other energy sources, such as oil or coal. However, it is not to be confused with gasoline, which is often shortened in colloquial usage to gas, especially in North America. Natural gas is measured in standard cubic meters or standard cubic feet. The density compared to air ranges from 0.58, 16.8 grams/mole, 0.71 kilograms per standard cubic meter, to as high as 0.79, 22.9 grams/mole, 0.97 kilograms per skm, but generally less than 0.64, 18.5 grams/mole, 0.78 kilograms per skm. For comparison, pure methane, 16.0425 grams/mole, has a density of 0.5539 times that of air, 0.678 kilograms per standard cubic meter. Natural gas can come out of the ground and cause a long burning fire. In ancient Greece, the gas flames at Mount Chimera contributed to the legend of the fire-breathing creature Chimera. In ancient China, gas resulting from the drilling for brines was first used by about 400 BC. The Chinese transported gas seeping from the ground in crude pipelines of bamboo to where it was used to boil salt water to extract the salt in the Ziliujing district of Sichuan. The discovery and identification of natural gas in the Americas happened in 1626. In 1821, William Hart successfully dug the first natural gas well at Fredonia, New York, United States, which led to the formation of the Fredonia Gas Light Company. The city of Philadelphia created the first municipally owned natural gas distribution venture in 1836. By 2009, 66,000 cubic kilometers, 16,000 mi3, or 8%, had been used out of the total 850,000 cubic kilometers, 200,000 mi3, of estimated remaining recoverable reserves of natural gas. In the 19th century, natural gas was primarily obtained as a byproduct of producing oil. The small, light gas carbon chains came out of this solution as the extracted fluids underwent pressure reduction from the reservoir to the surface, similar to uncapping a soft drink bottle where the carbon dioxide effervesces. The gas was often viewed as a byproduct, a hazard, and a disposal problem in active oil fields. The large volumes produced could not be used until relatively expensive pipelines and storage facilities were constructed to deliver the gas to consumer markets. Until the early part of the 20th century, most natural gas associated with oil was either simply released or burned off at oil fields. Gas vending and production flaring are still practiced in modern times, but efforts are ongoing around the world to retire them and replace them with other commercially viable and useful alternatives. Unwanted gas, or stranded gas without a market, is often returned to the reservoir with injection wells while awaiting a possible future market or to repressurize the formation, which can enhance oil extraction rates from other wells. In regions with a high natural gas demand, such as the U.S., pipelines are constructed when it is economically feasible to transport gas from a well site to an end consumer. In addition to transporting gas via pipelines for use in power generation, other end uses for natural gas include export as liquefied natural gas, LNG, or conversion of natural gas into other liquid products by gas to liquids, GTL. Technologies. GTL technologies can convert natural gas into liquid products such as gasoline, diesel, or jet fuel. A variety of GTL technologies have been developed, including FIS-Rotropsch, FAT, methanol to gasoline, MTG, and syngas to gasoline plus, STG plus. FAT produces synthetic crude that can be further refined into finished products, while MTG can produce synthetic gasoline from natural gas. STG Plus can produce drop-in gasoline, diesel, jet fuel, and aromatic chemicals directly from natural gas via a single-loop process. In 2011, Royal Dutch Shell's 140,000 barrels, 22,000 cubic meters, per day FAT plant went into operation in Qatar. Natural gas can be associated, found in oil fields, or non-associated, isolated in natural gas fields, and is also found in coal beds, as coal-bed methane. It sometimes contains a significant amount of ethane, propane, butane, and pentane, heavier hydrocarbons removed for commercial use before the methane is sold as a consumer fuel or chemical plant feedstock. Non-hydrocarbons such as carbon dioxide, nitrogen, helium, rarely, and hydrogen sulfide must also be removed before the natural gas can be transported. Natural gas extracted from oil wells is called casing head gas, whether or not truly produced up the annulus and through a casing head outlet, or associated gas. The natural gas industry is extracting an increasing quantity of gas from challenging, unconventional resource types, sour gas, tight gas, shale gas, and coal-bed methane. There is some disagreement on which country has the largest proven gas reserves. Sources that consider that Russia has by far the largest proven reserves include the U.S. Central Intelligence Agency, 47,600 cubic kilometers, and Energy Information Administration, 47,800 cubic kilometers, as well as the Organization of Petroleum Exporting Countries, 48,700 cubic kilometers. Contrarily, BP credits Russia with only 32,900 cubic kilometers, which would place it in second, slightly behind Iran, 33,100 to 33,800 cubic kilometers, depending on the source. It is estimated that there are about 900,000 cubic kilometers of unconventional gas such as shale gas, of which 180,000 cubic kilometers may be recoverable. In turn, many studies from MIT, Blackveatch, and the U.S. Department of Energy predict that natural gas will account for a larger portion of electricity generation and heat in the future. The world's largest gas field is the offshore South Pars, North Dome gas condensate field, shared between Iran and Qatar. It is estimated to have 51,000 cubic kilometers, 12,000 cubic miles, of natural gas and 50 billion barrels, 7.9 billion cubic meters, of natural gas condensates. Because natural gas is not a pure product, as the reservoir pressure drops when non-associated gas is extracted from a field under supercritical pressure/temperature conditions, the higher molecular weight components may partially condense upon isothermic depressurizing, an effect called retrograde condensation. The liquid thus formed may get trapped as the pores of the gas reservoir get depleted. One method to deal with this problem is to re-inject dried gas free of condensate to maintain the underground pressure and to allow re-evaporation and extraction of condensates. More frequently, the liquid condenses at the surface, and one of the tasks of the gas plant is to collect this condensate. The resulting liquid is called natural gas liquid, NGL, and has commercial value. Shale gas is natural gas produced from shale. Because shale has matrix permeability too low to allow gas to flow in economical quantities, shale gas wells depend on fractures to allow the gas to flow. Early shale gas wells depended on natural fractures through which gas flowed. Almost all shale gas wells today require fractures artificially created by hydraulic fracturing. Since 2000, shale gas has become a major source of natural gas in the United States and Canada. Because of increased shale gas production, the United States was 2014 the #1 natural gas producer in the world. The production of shale gas in the United States has been described as a shale gas revolution and as one of the landmark events in the 21st century. Following the increased production in the United States, shale gas exploration is beginning in countries such as Poland, China, and South Africa. Chinese geologists have identified the Sichuan Basin as a promising target for shale gas drilling, because of the similarity of shales to those that have proven productive in the United States. Production from the Way-201 well is between 10,000 and 20,000 cubic meters per day. In late 2020, China National Petroleum Corporation claimed daily production of 20 million cubic meters of gas from its Qingyuan demonstration zone. Town gas is a flammable gaseous fuel made by the destructive distillation of coal. It contains a variety of calorific gases including hydrogen, carbon monoxide, methane, and other volatile hydrocarbons, together with small quantities of non-calorific gases such as carbon dioxide and nitrogen, and was used in a similar way to natural gas. This is a historical technology and is not usually economically competitive with other sources of fuel gas today. Most town gas houses located in the eastern U.S. in the late 19th and early 20th centuries were simple byproduct coke ovens that heated bituminous coal in airtight chambers. The gas driven off from the coal was collected and distributed through networks of pipes to residences and other buildings where it was used for cooking and lighting. Gas heating did not come into widespread use until the last half of the 20th century. The coal tar, or asphalt, collected in the bottoms of the gashouse ovens was often used for roofing and other waterproofing purposes, and when mixed with sand and gravel was used for paving streets. Huge quantities of natural gas, primarily methane, exist in the form of clathrates under sediment on offshore continental shelves and on land in Arctic regions that experience permafrost, such as those in Siberia. Hydrates require a combination of high pressure and low temperature to form. In 2013, Japan Oil, Gas and Metals National Corporation, JOGMEC, announced that they had recovered commercially relevant quantities of natural gas from methane hydrate. As of mid-2020, natural gas production in the U.S. had peaked 3 times, with current levels exceeding both previous peaks. It reached 24.1 trillion cubic feet per year in 1973, followed by a decline, and reached 24.5 trillion cubic feet in 2001. After a brief drop, withdrawals increased nearly every year since 2006, owing to the shale gas boom, with 2017 production at 33.4 trillion cubic feet and 2019 production at 40.7 trillion cubic feet. After the third peak in December 2019, extraction continued to fall from March onward due to decreased demand caused by the COVID-19 pandemic in the U.S. The 2021 global energy crisis was driven by a global surge in demand as the world quit the economic recession caused by COVID-19, particularly due to strong energy demand in Asia. Because of its low density, it is not easy to store natural gas or transport it by vehicle. Natural gas pipelines are impractical across oceans since the gas needs to be cooled down and compressed, as the friction in the pipeline causes the gas to heat up. Many existing pipelines in the U.S. are close to reaching their capacity, prompting some politicians representing northern states to speak of potential shortages. The large trade cost implies that natural gas markets are globally much less integrated, causing significant price differences across countries. In Western Europe, the gas pipeline network is already dense. New pipelines are planned or under construction in Eastern Europe and between gas fields in Russia, Near East and Northern Africa, and Western Europe. Whenever gas is bought or sold at custody transfer points, rules and agreements are made regarding the gas quality. These may include the maximum allowable concentration of CO2, H2S and H2O. Usually, sales quality gas that has been treated to remove contamination is traded on a dry gas basis and is required to be commercially free from objectionable odors, materials, and dust or other solid or liquid matter, waxes, gums, and gum-forming constituents, which might damage or adversely affect the operation of equipment downstream of the custody transfer point. LNG carriers transport liquefied natural gas, LNG, across oceans, while tank trucks can carry liquefied or compressed natural gas, CNG, over shorter distances. Sea transport using CNG carrier ships that are now under development may be competitive with LNG transport in specific conditions. Gas is turned into liquid at a liquefaction plant, and is returned to gas form at the regasification plant at the terminal. Shipborne regasification equipment is also used. LNG is the preferred form for long-distance, high-volume transportation of natural gas, whereas pipeline is preferred for transport for distances up to 4,000 kilometers, 2,500 miles, over land and approximately half that distance offshore. CNG is transported at high pressure, typically above 200 bars, 20,000 kilopascals, 2,900 pounds per square inch. Compressors and decompression equipment are less capital-intensive and may be economical in smaller unit sizes than liquefaction. Regasification plants, natural gas trucks and carriers may transport natural gas directly to end users, or distribution points such as pipelines. In the past, the natural gas which was recovered in the course of recovering petroleum could not be profitably sold and was simply burned at the oil field in a process known as flaring. Flaring is now illegal in many countries. Additionally, higher demand in the last 28-30 years has made the production of gas associated with oil economically viable. As a further option, the gas is now sometimes re-injected into the formation for enhanced oil recovery by pressure maintenance, as well as miscible or miscible flooding. Conservation, re-injection, or flaring of natural gas associated with oil is primarily dependent on proximity to markets, pipelines, and regulatory restrictions. Natural gas can be indirectly exported through the absorption of other physical output. A recent study suggests that the expansion of shale gas production in the U.S. has caused prices to drop relative to other countries. This has caused a boom in energy-intensive manufacturing sector exports, whereby the average dollar unit of U.S. manufacturing exports has almost tripled its energy content between 1996 and 2012. A master gas system was invented in Saudi Arabia in the late 1970s, ending any necessity for flaring. Satellite and nearby infrared camera observations, however, show that flaring and venting are still happening in some countries. Natural gas is used to generate electricity and heat for desalination. Similarly, some landfills that also discharge methane gases have been set up to capture the methane and generate electricity. Natural gas is often stored underground inside depleted gas reservoirs from previous gas wells, salt domes, or in tanks as liquefied natural gas. The gas is injected in a time of low demand and extracted when demand picks up. Storage nearby end users help to meet volatile demands, but such storage may not always be practicable. With 15 countries accounting for 84% of the worldwide extraction, access to natural gas has become an important issue in international politics, and countries vie for control of pipelines. In the first decade of the 21st century, Gazprom, the state-owned energy company in Russia, engaged in disputes with Ukraine and Belarus over the price of natural gas, which has created concerns that gas deliveries to parts of Europe could be cut off for political reasons. The United States is preparing to export natural gas. Floating liquefied natural gas, FLNG, is an innovative technology designed to enable the development of offshore gas resources that would otherwise remain untapped due to environmental or economic factors which currently make them impractical to develop via a land-based LNG operation. FLNG technology also provides several environmental and economic advantages. Environmental: because all processing is done at the gas field, there is no requirement for long pipelines to shore, compression units to pump the gas to shore, dredging and jetty construction, and onshore construction of an LNG processing plant, which significantly reduces the environmental footprint. Avoiding construction also helps preserve marine and coastal environments. In addition, environmental disturbance will be minimized during decommissioning because the facility can easily be disconnected and removed before being refurbished and redeployed elsewhere. Economic: where pumping gas to shore can be prohibitively expensive, FLNG makes development economically viable. As a result, it will open up new business opportunities for countries to develop offshore gas fields that would otherwise remain stranded, such as those offshore East Africa. Many gas and oil companies are considering the economic and environmental benefits of floating liquefied natural gas, FLNG. There are currently projects underway to construct 5 FLNG facilities. Petronas is close to completion on their FLNG at Daewoo Shipbuilding and Marine Engineering and are underway on their FLNG-2 project at Samsung Heavy Industries. Shell Prelude is due to start production in 2017. The Browse LNG project will commence feed in 2019. Natural gas is primarily used in the Northern Hemisphere. North America and Europe are major consumers. Often wellhead gases require the removal of various hydrocarbon molecules contained within the gas. Some of these gases include heptane, pentane, propane, and other hydrocarbons with molecular weights above methane, CH4. The natural gas transmission lines extend to the natural gas processing plant or unit which removes the higher molecular weight hydrocarbons to produce natural gas with energy content between 35–39 megajoules per cubic meter, 958–1050 British thermal units per cubic foot. The processed natural gas may then be used for residential, commercial, and industrial uses. Natural gas flowing in the distribution lines is called midstream natural gas and is often used to power engines that rotate compressors. These compressors are required in the transmission line to pressurize and repressurize the midstream natural gas as the gas travels. Typically, natural gas-powered engines require 35–39 megajoules/M3, 958–1050 BTUs per cubic foot. Natural gas to operate at the rotational nameplate specifications. Several methods are used to remove these higher molecular weighted gases for use by the natural gas engine. A few technologies are as follows: Thomson skid cryogenic or chiller system, chemical enzymology system, a gas-fired power plant or gas-fired power station or natural gas power plant is a thermal power station that burns natural gas to generate electricity. Natural gas power stations generate almost a quarter of world electricity and a significant part of global greenhouse gas emissions and thus climate change. However, They can provide seasonal dispatchable generation to balance variable renewable energy where hydropower interconnectors are not available. Natural gas dispensed in a residential setting can generate temperatures over 1108 degrees C, 2008 degrees F, making it a powerful domestic cooking and heating fuel. In much of the developed world, it is supplied through pipes to homes, where it is used for many purposes including ranges and ovens, heating, cooling, and central heating. Heaters in homes and other buildings may include boilers, furnaces, and water heaters. Both North America and Europe are major consumers of natural gas. Domestic appliances, furnaces, and boilers use low pressure, usually with the standard pressure of around 1.7 kilopascals, 0.25 pounds per square inch, over atmospheric pressure. The pressures in the supply lines vary, either the standard utilization pressure, up, mentioned above, or elevated pressure, EP, which may be anywhere from 7 to 800 kilopascals, 1 to 120 pounds per square inch, over atmospheric pressure. Systems using EP have a regulator at the service entrance to step down the pressure to up. Natural gas piping systems inside buildings are often designed with pressures of 14 to 34 kilopascals, 2 to 5 pounds per square inch, and have downstream pressure regulators to reduce pressure as needed. The maximum allowable operating pressure for natural gas piping systems within a building is based on NFPA 54, National Fuel Gas Code, except when approved by the Public Safety Authority or when insurance companies have more stringent requirements. Generally, natural gas system pressures are not allowed to exceed 5 sig, 34.5 kilopascals, unless all of the following conditions are met. The AHJ will allow a higher pressure. The distribution pipe is welded. Note, 2. Some jurisdictions may also require that welded joints be radiographed to verify continuity. The pipes are closed for protection and placed in a ventilated area that does not allow gas accumulation. The pipe is installed in the areas used for industrial processes, research, storage, or mechanical equipment rooms. Generally, a maximum liquefied petroleum gas pressure of 20 sig, 138 kilopascals, is allowed, provided the building is used specifically for industrial or research purposes and is constructed by NFPA 58, Liquefied Petroleum Gas Code, Chapter 7. A seismic earthquake valve operating at a pressure of 55 sig, 3.7 bar, can stop the flow of natural gas into the site-wide natural gas distribution piping network that runs outdoors underground, above building roofs, and/or within the upper supports of a canopy roof. Seismic earthquake valves are designed for use at a maximum of 60 sig. In Australia, natural gas is transported from gas processing facilities to regulator stations via transmission pipelines. Gas is then regulated down to distributed pressures and the gas is distributed around a gas network via gas mains. Small branches from the network, called services, connect individual domestic dwellings, or multi-dwelling buildings to the network. The networks typically range in pressure from 7 kilopascals, low pressure, to 515 kilopascals, high pressure. Gas is then regulated down to 1.1 kilopascals or 2.75 kilopascals, before being metered and passed to the consumer for domestic use. Natural gas mains are made from a variety of materials, historically cast iron, though more modern mains are made from steel or polyethylene. In the U.S., compressed natural gas, CNG, is available in some rural areas as an alternative to less expensive and more abundant LPG, liquefied petroleum gas, the dominant source of rural gas. It is used in homes lacking direct connections to public utility-provided gas, or to fuel portable grills. Natural gas is also supplied by independent natural gas suppliers through natural gas choice programs throughout the United States. CNG is a cleaner and also cheaper alternative to other automobile fuels such as gasoline, petrol. By the end of 2014, there were over 20 million natural gas vehicles worldwide, led by Iran, 3.5 million, China, 3.3 million, Pakistan, 2.8 million, Argentina, 2.5 million, India, 1.8 million, and Brazil, 1.8 million. The energy efficiency is generally equal to that of gasoline engines, but lower compared with modern diesel engines. Gasoline, petrol vehicles converted to run on natural gas suffer because of the low compression ratio of their engines, resulting in a cropping of delivered power while running on natural gas, 10–15%. CNG-specific engines, however, use a higher compression ratio due to this fuel's higher octane number of 120–130. Besides being used in road vehicles, CNG can also be used in aircraft. Compressed natural gas has been used in some aircraft like the Aviat aircraft Husky 200 CNG and the Cromerat VX-1 Kitty Hawk LNG is also being used in aircraft. Russian aircraft manufacturer Tupolev, for instance, is running a development program to produce LNG and hydrogen-powered aircraft. The program has been running since the mid-1970s and seeks to develop LNG and hydrogen variants of the Tu-204 and Tu-334 passenger aircraft, and also the Tu-330 cargo aircraft, depending on the current market price for jet fuel and LNG. Fuel for an LNG-powered aircraft could cost 5,000 rubles, $100 less per ton, roughly 60%, with considerable reductions to carbon monoxide, hydrocarbon, and nitrogen oxide emissions. The advantages of liquid methane as a jet engine fuel are that it has more specific energy than the standard kerosene mixes do, and that its low temperature can help cool the air that the engine compresses for greater volumetric efficiency, in effect replacing an intercooler. Alternatively, it can be used to lower the temperature of the exhaust. Natural gas is a major feedstock for the production of ammonia, via the Haber process, for use in fertilizer production. The development of synthetic nitrogen fertilizer has significantly supported global population growth. It has been estimated that almost half the people on Earth are currently fed as a result of synthetic nitrogen fertilizer use. Natural gas can be used to produce hydrogen, with one common method being the hydrogen reformer. Hydrogen has many applications. It is a primary feedstock for the chemical industry, a hydrogenating agent, an important commodity for oil refineries, and a fuel source in hydrogen vehicles. Protein-rich animal and fish feed are produced by feeding natural gas to Methylococcus capsulatus bacteria on a commercial scale. Natural gas is also used in the manufacture of fabrics, glass, steel, plastics, paint, synthetic oil, and other products. The first step in the valorization of natural gas components is usually the of the alkane into olefin. The oxidative dehydrogenation of ethane leads to ethylene, which can be converted further to ethylene epoxide, ethylene glycol, acetaldehyde, or other olefins. Propane can be converted to propylene or can be oxidized to acrylic acid and acrylonitrile. Human activity is responsible for about 60% of all methane emissions and most of the resulting increase in atmospheric methane. Natural gas is intentionally released or is otherwise known to leak during the extraction, storage, transportation, and distribution of fossil fuels. Globally, methane accounts for an estimated 33% of anthropogenic greenhouse gas warming. That decomposition of municipal solid waste, a source of landfill gas, and wastewater accounts for an additional 18% of such emissions. These estimates include substantial uncertainties which should be reduced shortly with improved satellite measurements, such as those planned for methane SAT. After releasing to the atmosphere, methane is removed by gradual oxidation to carbon dioxide and water by hydroxyl radicals, OA, formed in the troposphere or stratosphere, giving the overall chemical reaction CH4 plus 2O2 ACO2 plus 2H2O. While the lifetime of atmospheric methane is relatively short when compared to carbon dioxide, with a half-life of about 7 years, it is more efficient at trapping heat in the atmosphere, so that a given quantity of methane has 84 times the global warming potential of carbon dioxide over 20 years and 28 times over 100 years. Natural gas is thus a potent greenhouse gas due to the strong radiative forcing of methane in the short term, and the continuing effects of carbon dioxide in the longer term. Targeted efforts to reduce warming quickly by reducing anthropogenic methane emissions is a climate change mitigation strategy supported by the Global Methane Initiative. When refined and burned, natural gas can produce 25–30% less carbon dioxide per joule delivered than oil, and 40–45% less than coal. It can also produce potentially fewer toxic pollutants than other hydrocarbon fuels. However, compared to other major fossil fuels, natural gas causes more emissions in relative terms during the production and transportation of the fuel, meaning that the life cycle greenhouse gas emissions are about 50% higher than the direct emissions from the site of consumption. In terms of the warming effect over 100 years, natural gas production and use comprise about 1/5 of human greenhouse gas emissions, and this contribution is growing rapidly. Globally, natural gas use emitted about 7.8 billion tons of CO2 in 2020, including flaring, while coal and oil use emitted 14.4 and 12 billion tons, respectively. The estimates the energy sector, oil, natural gas, coal, and bioenergy, to be responsible for about 40% of human methane emissions. According to the IPCC Sixth Assessment Report, natural gas consumption grew by 15% between 2015 and 2019, compared to a 5% increase in oil and oil product consumption. The continued financing and construction of new gas pipelines indicate that huge emissions of fossil greenhouse gases could be locked in for 40 to 50 years into the future. In the U.S. state of Texas alone, 5 new long-distance gas pipelines have been under construction, with the first entering service in 2019, and the others scheduled to come online during 2028–2022. To reduce its greenhouse emissions, the Netherlands is subsidizing a transition away from natural gas for all homes in the country by 2050. In Amsterdam, no new residential gas accounts have been allowed since 2018, and all homes in the city are expected to be converted by 2040 to use the excess heat from adjacent industrial buildings and operations. Some cities in the United States have started prohibiting gas hookups for new houses, with state laws passed and under consideration to either require electrification or prohibit local requirements. The UK government is also experimenting with alternative home heating technologies to meet its climate goals. To preserve their businesses, natural gas utilities in the United States have been lobbying for laws preventing local electrification ordinances, and are promoting renewable natural gas and hydrogen fuel. Although natural gas produces far lower amounts of sulfur dioxide and nitrogen oxides, NOx, than other fossil fuels, NOx from burning natural gas in homes can be a health hazard. Natural gas extraction also produces radioactive isotopes of polonium, Po-210, lead, Pb-210, and radon, Rn-220. Radon is a gas with initial activity from 5 to 200,000 becquerels per cubic meter of gas. It decays rapidly to Pb-210, which can build up as a thin film in gas extraction equipment. The natural gas extraction workforce faces unique health and safety challenges. Some gas fields yield sour gas containing hydrogen sulfide, H2S, a toxic compound when inhaled. Gas treating, an industrial-scale process that removes acidic gaseous components, is often used to remove hydrogen sulfide from natural gas. The extraction of natural gas, or oil, leads to a decrease in pressure in the reservoir. Such a decrease in pressure in turn may result in subsidence, and sinking of the ground above. Subsidence may affect ecosystems, waterways, sewer and water supply systems, foundations, and so on. Releasing natural gas from subsurface porous rock formations may be accomplished by a process called hydraulic fracturing or fracking. Since the first commercial hydraulic fracturing operation in 1949, approximately 1 million wells have been hydraulically fractured in the United States. The production of natural gas from hydraulically fractured wells has used the technological developments of directional and horizontal drilling, which improved access to natural gas in tight rock formations. Strong growth in the production of unconventional gas from hydraulically fractured wells occurred between 2000 and 2012. In hydraulic fracturing, Well operators force water mixed with a variety of chemicals through the wellbore casing into the rock. The high-pressure water breaks up or fracks the rock, which releases gas from the rock formation. Sand and other particles are added to the water as a proppant to keep the fractures in the rock open, thus enabling the gas to flow into the casing and then to the surface. Chemicals are added to the fluid to perform such functions as reducing friction and inhibiting corrosion. After the frac, oil or gas is extracted and 30–70% of the frac fluid, that is the mixture of water, chemicals, sand, etc., flows back to the surface. Many gas-bearing formations also contain water, which will flow up to the wellbore to the surface along with the gas. In both hydraulically fractured and non-hydraulically fractured wells, this produced water often has a high content of salt and other dissolved minerals that occur in the formation. The volume of water used to hydraulically fracture wells varies according to the hydraulic fracturing technique. In the United States, the average volume of water used per hydraulic fracture has been reported as nearly 7,375 gallons for vertical oil and gas wells before 1953, nearly 197,000 gallons for vertical oil and gas wells between 2000 and 2010, and nearly 3 million gallons for horizontal gas wells between 2000 and 2010. Determining which fracking technique is appropriate for good productivity depends largely on the properties of the reservoir rock from which to extract oil or gas. If the rock is characterized by low permeability A, which refers to its ability to let substances, that is gas, pass through it, then the rock may be considered a source of tight gas. Fracking for shale gas, which is currently also known as a source of unconventional gas, involves drilling a borehole vertically until it reaches a lateral shale rock formation, at which point the drill turns to follow the rock for hundreds or thousands of feet horizontally. In contrast, conventional oil and gas sources are characterized by higher rock permeability, which naturally enables the flow of oil or gas into the wellbore with less intensive hydraulic fracturing techniques than the production of tight gases required. The decades of the development of drilling technology for conventional and unconventional oil and gas production have not only improved access to natural gas in low permeability reservoir rocks but also poses significant adverse impacts on environmental and public health. The US EPA has acknowledged that toxic, carcinogenic chemicals, that is benzene and ethylbenzene, have been used as gelling agents in water and chemical mixtures for high-volume horizontal fracturing, HVHF. Following the hydraulic fracture in HVHF, the water, chemicals, and frac fluid that returns to the well's surface, called flowback or produced water, may contain radioactive materials, heavy metals, natural salts, and hydrocarbons that exist naturally in shale rock formations. Fracking chemicals, radioactive materials, heavy metals, and salts that are removed from the HVHF well by good operators are so difficult to remove from the water they are mixed with, and would so heavily pollute the water cycle, that most of the flowback is either recycled into other fracking operations or injected into deep underground wells, eliminating the water that HVHF required from the hydrologic cycle. Historically low gas prices have delayed the nuclear renaissance, as well as the development of solar thermal energy. Natural gas in its native state is colorless and almost odorless. To assist consumers in detecting leaks, an odorizer with the scent similar to rotten eggs, start butylthiol, T-butyl mercaptan, is added. Sometimes a related compound, thiophane, may be used in the mixture. Situations in which an odorant that is added to natural gas can be detected by analytical instrumentation, but cannot be properly detected by an observer with a normal sense of smell, have occurred in the natural gas industry. This is caused by odor masking when one odorant overpowers the sensation of another. As of 2011, the industry is conducting research on the causes of odor masking. Explosions caused by natural gas leaks occur a few times each year. Individual homes, small businesses, and other structures are most frequently affected when an internal leak builds up gas inside the structure. Leaks often result from excavation work, such as when contractors dig and strike pipelines, sometimes without knowing any damage resulted. Frequently, The blast is powerful enough to significantly damage a building but leave it standing. In these cases, the people inside tend to have minor to moderate injuries. Occasionally, the gas can collect in high enough quantities to cause a deadly explosion, destroying one or more buildings in the process. Many building codes now forbid the installation of gas pipes inside cavity walls or below floorboards to mitigate against this risk. Gas usually dissipates readily outdoors, but can sometimes collect in dangerous quantities if flow rates are high enough. However, considering the tens of millions of structures that use the fuel, the individual risk of using natural gas is low. Natural gas heating systems may cause carbon monoxide poisoning if unvented or poorly vented. Improvements in natural gas furnace designs have greatly reduced CO poisoning concerns. Detectors are also available that warn of carbon monoxide or explosive gases such as methane and propane. Quantities of natural gas are measured in standard cubic meters. Cubic meter of gas at temperature 15A degrees C, 59A degrees F, and pressure 101.325 kilopascals, 14.6959 pounds per square inch, or standard cubic feet. Cubic foot of gas at temperature 60.08 degrees F and pressure 14.73 pounds per square inch, 101.6 kilopascals. 1 standard cubic meter equals 35.301 standard cubic feet. The gross heat of combustion of commercial quality natural gas is around 39 megajoules/m3, 0.31 kilowatt-hours per cubic foot, but this can vary by several percent. This is about 50 to 54 megajoules/kg depending on the density. For comparison, the heat of combustion of pure methane is 37.7 megajoules per standard cubic meter or 55.5 megajoules/kg. Except in the European Union, the US, and Canada, natural gas is sold in gigajoule retail units. LNG, liquefied natural gas, and LPG, liquefied petroleum gas, are traded in metric tons, 1,000 kilograms, or million BTU as spot deliveries. Long-term natural gas distribution contracts are signed in cubic meters, and LNG contracts are in metric tons. The LNG and LPG are transported by specialized transport ships, as the gas is liquefied at cryogenic temperatures. The specification of each LNG, LPG cargo will usually contain the energy content, but this information is in general not available to the public. The European Union aims to cut its gas dependency on Russia by 2/3 in 2022. In August 2015, possibly the largest natural gas discovery in history was made and notified by an Italian gas company Eni. The energy company indicated that it has unearthed a supergiant gas field in the Mediterranean Sea covering about 40 square miles. 100 square kilometers. This was named the Zohr gas field and could hold a potential 30 trillion cubic feet, 850 billion cubic meters, of natural gas. Eni said that the energy is about 5.5 billion barrels of oil equivalent, BO, 3.48 tilde, 1010 gigajoules. The Zohr field was found in the deep waters off the northern coast of Egypt, and Eni claims that it will be the largest ever in the Mediterranean and even the world. Gas prices for end users vary greatly across the EU. A single European energy market, one of the key objectives of the EU, should level the prices of gas in all EU member states. Moreover, it would help to resolve supply and global warming issues, as well as strengthen relations with other Mediterranean countries and foster investments in the region. Qatar has been asked by the US to supply emergency gas to the EU in case of supply disruptions in the Russo-Ukrainian crisis. In US units, 1 standard cubic foot, 28 liters, of natural gas produces around 1,028 British thermal units, 1,085 kilojoules. The actual heating value when the water formed does not condense is the net heat of combustion and can be as much as 10% less. In the United States, retail sales are often in units of therms, th. 1 therm equals 100,000 BTUs. Gas sales to domestic consumers are often in units of 100 standard cubic feet, SCF. Gas meters measure the volume of gas used, and this is converted to therms by multiplying the volume by the energy content of the gas used during that period. which varies slightly over time. The typical annual consumption of a single-family residence is 1,000 terms or 1 residential customer equivalent, RCE. Wholesale transactions are generally done in decatherms, 500, 1,000 decatherms, 1,500, or million decatherms, 2,500. A million decatherms is a trillion BTU, roughly a billion cubic feet of natural gas. The price of natural gas varies greatly depending on location and type of consumer. The typical caloric value of natural gas is roughly 1,000 BTUs per cubic foot, depending on the gas composition. Natural gas in the United States is traded as a futures contract on the New York Mercantile Exchange. Each contract is for 10,000 million BTU or 10 billion BTU, 10,551 gigajoules. Thus, if the price of gas is $10/million BTU on the NYMEX, the contract is worth $100,000. Canada uses metric measures for the internal trade of petrochemical products. Consequently, natural gas is sold by the gigajoule, GJ, cubic meter, M3, or 1,000 cubic meters, E3 M3. Distribution infrastructure and meters almost always meter volume, cubic foot or cubic meter. Some jurisdictions, such as Saskatchewan, sell gas by volume only. In other jurisdictions, such as Alberta, gas is sold by energy content, GJ. In these areas, almost all meters for residential and small commercial customers measure volume, M3 or FT3, and billing statements include a multiplier to convert the volume to the energy content of the local gas supply. A gigajoule, GJ, is a measure approximately equal to 80 liters, 0.5 barrels, of oil, or 28 cubic meters or 1,000 cubic feet or 1 million BTUs of gas. The energy content of the gas supply in Canada can vary from 37 to 43 megajoules/M3, 990 to 1,150 BTUs per cubic foot, depending on the gas supply and processing between the wellhead and the customer. Natural gas may be stored by adsorbing it to porous solids called sorbents. The optimal condition for methane storage is at room temperature and atmospheric pressure. Pressures up to 4 megapascals, about 40 times atmospheric pressure, will yield greater storage capacity. The most common sorbent used for ANG is activated carbon, AAC, primarily in 3 forms: activated carbon fiber, ACF, powdered activated carbon, PAC, and activated carbon monolith.